Hello everyone. In this video, I'm going to talk with you about something called statistical power, and then we're going to end up with just a little bit of a review in this last video of the series. So in this section, we're going to define statistical power and identify the 3 steps in determining statistical power. So what is statistical power? It is the probability that a test will correctly reject the null hypothesis. It's the probability that a test will identify a treatment effect if one really exists. So it's the ability to find a treatment effect and at the same time balance the risk of making a type 1 error. So the first step is to identify the treatment. What is it that we are going to be manipulating? We identify the null hypothesis and then we locate our critical region. These are the first steps in identifying statistical power. So power is that proportion of the distribution that is located beyond the critical boundary. We've been referring to this as the critical value, but it is the power of a statistical test. So you see in this case, 2 different types of tests are here, a one-tailed test and a two-tailed test. The shaded areas are statistical power. That is the power of the test that we are conducting. So as the size of a treatment effect increases, statistical power also increases. And the researcher can control some factors. When we have a larger alpha, that increases the power of the test. For example, when we have a 0.05 critical boundary versus a 0.01, that power area is greater. A one-tailed test has more power than a two-tailed test, and I'm going to illustrate that in just a moment. And then larger sample sizes have more power than smaller sample sizes. So let's take a look at one-tailed versus a two-tailed test for power. So the one-tailed test is on the left and the two-tailed test is on the right. Both tests have a preset alpha of 0.05. But in a one-tailed test, you've loaded all of that 0.05 in one tail. So we do this when we have a pretty strong suspicion that our test result is going to be in one tail or another. And this strong suspicion is something that is informed by prior research. So let's just say I pretty much know that I'm going to have a positive effect, that my mean is going to be above the population mean. Then I could conduct a one-tailed test. And in doing so, I take that power that was split up between 2 tails and I load it all on one tail. It gives me more statistical power in my statistical test. Two-tailed tests, as we've mentioned before, we take that 0.05 and we split it between the 2 tails. And as a reminder, we do this when we don't know in which direction our results are going to be. Maybe we might think that they're positive, but they could be negative too, and in which case we need to be prepared for an extreme result in either tail. So we have a one-tailed test that has more statistical power just based on the fact that all of the critical area is in one tail. So if you're going to do a one-tailed test, it needs to be stated a priori, which means we need to say up front, I have a strong reason to believe that my results will either be positive or negative. It has to be justified. And we can't change our mind after we do the statistical test if it ends up that our results are in the other tail. This is part of being ethical and objective in our research. We set our alpha up front and we set whether it's a one-tailed test or a two-tailed test are going to be conducted up front. And if we have no support for doing a one-tailed test, then we have to do a two-tailed test. And sometimes people do a two-tailed test just because it's a more rigorous test too. It's harder to get to a significance level of over plus or minus 1.96 than it is 1.645, for example. A one-tailed test uses a special hypothesis known as a directional hypothesis. And you can take a look here to see how it looks different than when we are doing a non-directional or a two-tailed test. With a directional hypothesis, we're specifying a direction that we think the result will be in. So let's try a learning check to see if you have a grasp of this non-directional versus directional tests. So this asks us to find the critical boundary at alpha 0.05 for the hypotheses. And as we look at these hypotheses, they are not a two-tailed test. These are examples of hypotheses for a one-tailed test, meaning that all the alpha is going to be clustered up on one side. Now, the hypothesis is saying, for the null hypothesis, that the mu is greater than 27. The alternative hypothesis is saying that the mu is going to be less than or equal to 27. So we are specifying that we think that there's going to be a difference where the answer is going to be less than 27. So we're looking for something that's going to be less than. That gives us a clue that we're going to be looking for a negative z-score. Now, the next thing we're going to be doing is looking at the alpha of 0.05. We know that when alpha of 0.05 is split between two tails, we have positive and negative 1.96. But when it is clustered all in one tail, if you look at your z table, you will see for 5% in the tail, 1.65. But since we're hypothesizing in our alternative hypothesis that our mean is going to be less than 27, we are looking at a negative number. So negative 1.65 is going to be our answer. It's a directional hypothesis, and it's going to be below the mean. We're hypothesizing on the alternative side that it's going to be below the mean. Let's try another one. Find the critical boundary at 0.05 for these hypotheses. The null is that the mu is equal to 52, and the alternative is that the mu is not equal to 52. Well, this is going to be more familiar because this is the type of non-directional two-tailed hypotheses that we've been dealing with. So we are familiar with this. We know that when we have alpha at 0.05 for a two-tailed test, 1.96 is our z-score. But not just that. Since it is two-tailed, it needs to be plus or minus 1.96. This is not a directional hypothesis, and the alternative states that the mean will not be equal to the mean. It's not saying that it's going to be higher or lower. Okay? Let's try another one. Find the critical boundary at alpha equals 0.01 for these hypotheses. The mu is greater than, mu is less than 17, or the mu is greater than or equal to 17. Okay. This is a directional hypothesis. And so we're going to get rid of this plus or minus 2.58. We know it's not going to be in both tails. So what we need to do is we need to look at our z table for 1% in the tail. So we're looking for, and if you want to pause your video and take out your z table and look at that, we're looking for 1% in the tail. So 1% in the tail is equal to a z of 2.33. Now let's look at the direction of our hypothesis. The alternative hypothesis says that the mean is going to be greater than or equal to 17. So we're looking for a positive result. And so our answer then is a positive 2.33. Again, this is a directional hypothesis, and the alternative says that the mean is going to be higher than the population mean. Okay, so let's try something else. The results of a one-tailed hypothesis test produced a z of 1.79. Based on this result, what is the correct statistical decision? And it's asking you to evaluate it based on an alpha of 0.05 and an alpha of 0.01. So what we need to do first is realize that it's a one-tailed test. So we need to look at our z table for 5% in the tail, because 5% is all going to be in one tail. 5% in the tail is equal to a z-score of 1.65. It's technically 1.645. We're calling it 1.65. So what is the percent in the tail, 1% in the tail, in the z table for 0.01? Well, 1% in the tail is 2.33. So at 0.05, we have a z of 1.65, and at 0.01, we have a z of 2.33. Our test produced a z of 1.79. So that is more extreme than 0.05 at 1.65. It's less extreme than 0.01 with a z of 2.33. So our correct answer is going to be that we're going to reject the null at 0.05, but not with an alpha of 0.01. All right, this is it. These are the videos for this week. I hope that you come to me with questions that you have. Bring questions to the hallway conversation. I look forward to hearing from you.